Dr. Habib Najm from Sandia National Labs, where he's a distinguished member of the technical staff. Dr. Najm leads a research program in computational reacting flow and insertion to quantification. His research is broad-ranging and has spanned development of numerical methods for reacting flow computations, computational studies of laminar flames with detailed chemical kinetics, development of uncertainty quantification methods and their application in reacting flow, analysis and reduction of multi-scale chemical systems, modeling electrochemical microfluid systems, statistical data analysis for biodetection, statistical systems, and Bayesian inference methods for inverse problems. So without further ado, I'd like to hand it over to Habib to help us learn more on the topic of uncertainty quantification in computational models of physical systems.
Thank you, Lorraine. And also thank you for those present. I will try to give a picture of the uncertain quantification field as it applies specifically to computational models of physical systems. And I will go over various methods and their applications in different scenarios, and try to point out interesting aspects of the field as well as challenges going forward. This work has been the result of many years of research funded by the Department of Energy, various offices presented below, and has been always in collaboration with a number of people both at Sandia and at universities elsewhere. So let's start with the essential picture of computational modeling is that one has in principle some code, maybe a large PDE solver, could be a climate code or a code for a combustion system or a jet. Any type of code will take inputs and give you certain outputs. And if you look at this computational model as a black box, you can imagine you write it y equal f of x, where x is the inputs and y is the set of outputs. And so we're quite comfortable with this picture that we have inputs to our models, which can be initial conditions, boundary conditions, or parameters, or other things, and some output predictions. And this is what we would call a forward problem. Of course, there's also the question of where the inputs come from, and these are typically based on measurements. And the act of measurement involves fitting, usually. You propose a model for the experiment and you fit it to the data, which gives you the best fit parameters that fit the model. And this is how you determine parameters that are input to some other model. For example, in the context of chemical modeling of combustion, the rate constants for the various reactions are what's in the parameter vector x, and these come from measurements. And the act of measurement is an inverse problem because you have this type of fitting. So the parameters that go into our model usually come from some type of measurement, either observation or empirical experiment, etc. And because data is usually noisy, there is uncertainty in the parameters that you infer from this data by fitting. And so I'm showing a PDF on x rather than the idea that x is a value. You have to think about x as an uncertain parameter. And so then, since x is input into the model, the output is also uncertain. And you could imagine that there's a PDF on y. So this is a primary source of uncertainty in our computations, and one can imagine others, but this is a very clear indication of where uncertainty comes into computations that we might do on a big machine. So there's this in being able to predict the uncertainty in our outputs, given that there are uncertainties in the inputs. Aside from that, even in a computational setting, if you have different models, and I show here the vector f1, f2, fn in terms of a vector of different models, and you want to compare them to data validation, again, data and the act of comparison for validation or hypothesis testing also needs to be done in a statistical setting. Uncertainty needs to be part of So this is why we worry about uncertainty, and there are other reasons, but this is an obvious reason. I want to go the methods that are used for uncertainty quantification in large computation models, and I will start with an introduction. Then I will describe the forward UQ problem, going from inputs to output, and also the inverse problem, the estimation of uncertain parameters given data. Okay, so the forward propagation, then consider y after x. If you had a small amount of uncertainty in the input, then certainly one immediately, obvious way of propagating this to the output is if you think of sensitivity and error propagation. Have the df derivative that is shown here, and you have a delta on x, then you can get a delta on y directly. Right? So you're able to use local sensitivity point x0 to be able to estimate uncertainty in the output given uncertainty. This because it's a linearized estimate, and it's based on a location at x0. This is okay for small degrees of, and also a small non-linearity in F. In general, if we have large input uncertainty or large amplification of uncertainty due to nonlinearity in F, then we need to use some different method. And there are a class of non-probabilistic methods that can come here. Certainly, these go under different fuzzy logic. There's use of evidence theory and interval math. I won't go into them. I will only address a large class of methods which fall under probability. The reason, frankly, is that probabilistic methods have found much more direct application in large models. They have straightforward use. Of course, it's not trivial to use them, but there's no questions about the setup of the problem with this context. So we'll deal with probabilistic context. We represent uncertain inputs or uncertain quantities in general using, excuse me,
I'm going to ask you to turn off
we represent uncertain quantities in general using probability theory. And I'm sorry, Lorraine, are you saying something to me? I'm sorry, I'll wait for Lorraine to answer. You want me to turn off my webcam? Okay. Okay. Can you still hear me, Lorraine? Okay. All right. Good. Thank you. All right. So considering probabilistic forward methods, we want to represent uncertain quantities using probability theory. And as random variables or random fields, etc. And so we have, obviously, one easy way of propagating uncertainty is to define a PDF on X. And if we generate random samples from P of X, and for each random sample of X, we solve the forward model. Then we have samples on Y, and we can bin them and get a PDF on Y. So obviously, this is an easy way of propagating uncertainty using Monte Carlo methods, feasible for large computationally expensive models because of the slow convergence of Monte Carlo and quasi-Monte Carlo methods. So it's important to think of how to deal with that complexity. One way to do it is to build a cheap surrogate for f of x. If you're able to construct, say, a response surface that represents the variation of y over x with a simple polynomial, then you can replace f of x with this response and you can do Monte Carlo. And this can be done by evaluating the forward model at different points over the range of x and using interpolants, for example, or by fitting a polynomial to these points. And in many ways, the methods I'm going to talk about are really trying to do that effectively. And specifically, there is a class of methods that we call Galerkin methods that, as opposed to what interpolants try to do, which is to find a surface that goes through the points, or fitting to directly fit the points, Galerkin methods essentially satisfy a form of the governing equations or evaluate a suitable projection on a set of functions of interest that are used as weight functions and that are relevant here. So I will. And the representation context is called the polynomial chaos, which is a very old word, has nothing to say with modern chaos theory, but it's a class of representation with polynomials for random variables and random fields. That's how to describe. We'll describe both non-intrusive PC methods. In other words, intrusive methods, you have to change the model, you have to change the code, you have to rewrite software, etc. Non-intrusive methods treat the forward model as a black box. Okay. So, one more thing before introducing polynomial chaos is to talk about the representation of the random variable. If we're talking about random variables, we can talk about them in or moments or characteristic function, or we could simply talk about them in the raw, if you like. A random variable, by definition, is simply a function on a probability space. And this is what we're going to do. We're going to deal with the random variables as functions and represent them using function representations. And advantages in terms of being able to propagate uncertainty. It does require that you have a restriction of finite variance, but we will accept that. Usually something that we would want anyway. And by doing this, you really can propagate uncertainty using functional analysis, which is the key advantage here. Okay, so polynomial chaos is a representation for random variables that is very much like Fourier expansion. And it comes out of, first, the representation of a random variable as a function. So the first step is to define what we call a germ, which is this set of standard random variables. This is a convenient set, for example, results of uniform, standard uniform. Considering probabilistic forward UQ methods, we want to represent uncertain quantities using probability theory. And as random variables or random fields, etc. And so we have, obviously, one easy way of propagating uncertainty is to define a PDF on X. And if we generate random samples from P of X, and for each random sample of X, we solve the forward model. Then we have samples on Y, and we can bin them and get a PDF on Y. So obviously, this is an easy way of propagating uncertainty using Monte Carlo methods, but it's not feasible for large computationally expensive models because of the slow convergence of Monte Carlo and quasi-Monte Carlo methods. So it's important to think of how to deal with that complexity. One way to do it is to build a cheap surrogate for f of x. If you're able to construct, say, a response surface that represents the variation of y over x with a simple polynomial, then you can replace f of x with this response surface and you can do Monte Carlo. And this can be done by evaluating the forward model at different points over the range of x and using interpolants, for example, or by fitting a polynomial to these points. And in many ways, the methods I'm going to talk about are really trying to do that effectively. And specifically, there is a class of methods that we call Galerkin methods that, as opposed to what interpolants try to do, which is to find a surface that goes through the points or fitting to directly fit the points, Galerkin methods essentially satisfy a weak form of the Gaussian equations or evaluate a suitable projection on a set of functions of interest that are used as weight functions and that are relevant here. So I will introduce that here. And the representation which we use in this context is called the Polynomial Chaos, which is a very old word, has nothing to say with modern chaos theory, but it's a class of representation with polynomials for random variables and random fields that I'll get to describe. And we'll describe both intrusive and non-intrusive PC methods. In other words, intrusive methods, you have to change the model, you have to change the code, you have to rewrite software, etc. Non-intrusive methods treat the forward model as a black box. Okay. So, one more thing before introducing polynomial chaos is to talk about the representation of the random variable. If we're talking about random variables, we can talk about them in terms of their density or moments or characteristic function, or we could simply talk about them in the raw, if you like. A random variable, by definition, is simply a function on a probability space. And this is what we're going to do. We're going to deal with the random variables as functions and represent them using functional representations. And this has advantages in terms of being able to propagate uncertainty. It does require that you have a restriction of finite variance, but we will accept that as usually something that we would want anyway. And by doing this, you really can propagate uncertainty using functional analysis methods, which is the key advantage here. Okay, so polynomial chaos is a representation for random variables that is very much like a Fourier expansion. And it comes out of, first, the representation of a random variable as a function. So the first step is to define what we call a germ, which is a set of standard random variables. This is a convenient set, for example, a set of standard normals or a set of standard uniform random variables that are independent. So you pick a germ, and there's technical restrictions on the germ, but in general, there's a very wide class of standard random variables that you can use. Having picked the vector C, now you say any random variable in the probability space generated by the sigma algebra corresponding to C. And this is a technical description or technical restriction that I won't go into now, but again, for most applications, it's not something we're concerned about. So any random variable in a particular class can be written as a polynomial chaos expansion. And the first step is to say that the random variable U is a function of Xi. And this statement that it is any random variable in this class can be written as a function of Xi is because of this sigma algebra definition. Once you say it's a function of Xi, then you can represent it as an expansion in terms of a set of polynomials that spans the space. And in this case, we're writing a sum with coefficients U sub k and functions C sub k of Xi. So very much like a Fourier expansion, this expansion has coefficients and has functions. The functions, as in Fourier representations, sines and cosines, which are orthogonal. These functions are not sines and cosines, but they're chosen to be a set of orthogonal functions with respect to the density of Xi. Okay. And the mode coefficients, again, as in Fourier series, they're found by projection. And so you take any function of Xi, you have an integral which provides a projection on mode K, weighted by the density of Xi, and that gives you the coefficient UK for each mode K. And this type of representation is quite general. It can represent any random variable in this space. It can have any density. And it can be based on different bases, as I said. If you choose the Gaussian basis, then the functions that are orthogonal with respect to the Gaussian are the Hermits, uniform, Legendre, etc. Okay. And the representation is easy to see in action. Here is a log normal random variable whose PDF is shown in red. And I want to represent it with a PCE. And I start with what's shown on the lower left, which is a first order PCE. And that has a PDF that's green, so it's obviously not a sufficiently good representation. But as I increase the order and I fit the coefficients appropriately, I can arrive at the representation for the random variable that has the density that I'm interested in. Okay, so it's important to see that what we're looking for is a representation of the random variable itself, not of its density. But we look for representation that has the right moments, it has the right density, etc. Okay, and you can see that by generating samples of Xi, which are easy to do since it's standard normal in this case, you can generate as many samples of U as you like. That's the essential idea. Okay, and random fields are also important to present, although I won't present them for much time. I won't spend much time here. A random variable is, by construction, a function on an event space. A random field is generally a function on a product space that has dependence, let's say, on space and time as well as density, as well as randomness. So, the temperature of sea surface water has a dependence on space and time, and it's also uncertain. That's a random field. A random field is more complex than a random variable, but frequently there's enough structure to be able to represent random fields efficiently. And specifically, there's this representation that's very much based on singular value decomposition ideas and principal component analysis, except this constructs a full random field representation. It's called the Carhoonen-Loewe expansion. Without going into detail, it basically relies on knowing the covariance function of the random field and its mean function, and then the eigenvalues and eigenfunctions of the covariance, as well as a set of random variables that are shown here, together constitute a representation using this, what's called the Carhoonen-Loewe expansion. The utility of this first is that it's an optimal representation. You can represent a random field in terms of finite number of degrees of freedom, in other words, finite number of etas, which are random variables here. So we can cut this infinity down because most random fields have certain degree of smoothness. And further, since these etas are random variables, we can represent each of them as a PCE, and so a random field overall can be represented as a PCE. So I won't go into more detail about that. Just as an illustration, a random field that has different length scales of variability or different correlation lengths has different structures. So here is a Gaussian random field in 2D, and short correlation length on the left, delta 0.1, tells you that you can find random variability on relatively small length scales, and as you go to delta 0.5, the random variability is on larger length scales. So if you know something locally, you know it pretty well nearby. It's only if you go far away that you really don't know it. Okay, so this is a smooth field. It has a large correlation length. And as I say, you represent these fields in terms of the eigenmodes of the covariance matrix. And again, they look differently for different deltas. Again, they're finer detail for a random field that has shorter correlation length. But the upshot is that what you look for is the decay rate of the eigenvalues of the random field. So a random field that has delta 0.5, which is smooth, the eigenvalues decay quickly, and so you can represent it accurately with a relatively small number of terms. Whereas one with delta 0.1, the eigenvalues decay slowly and you need many terms. So here, for example, delta 0.1, and we're plotting the random field and the KLE on top of it. And what you see is even with 64 terms, there's still mismatch between the blue contour lines and the gray below them. But if I go to delta 0.2, you see that now I have a match already by 64. Delta 0.5, even with 16 terms, I have a reasonably good representation, right? So you can represent it with a small number of degrees of freedom. Okay, so that's basically an introduction to the representation. How we use this representation of random variables and random fields in UQ is we represent the inputs using these types of expansions, and then we propagate them forward to evaluate similar expansion for the output. And the advantage is that you can do this efficiently. Yeah. Okay. So a few words about the different classes of methods for forward propagation. Intrusive methods, as I said, you have to look at changes in the model, in the codes, in the software, etc. So with intrusive methods, given any set of equations that has parameters lambda, and you solve for a quantity of interest u, you express the inputs as a PCE, you express the output as an unknown PCE whose coefficients are unknown. You substitute in the equations, and without detail, you apply Galerkin projection to the equations, so you satisfy them in the weak form, and you get a new set of equations for the vector lambda of coefficients, which is the coefficients of the for the vector capital U of coefficients, which is the coefficients of the unknown expansion for U. And you solve for capital U. So once you do that, you immediately have the PCE of the output, and you can do everything you want with it. So then the advantage of intrusive methods, I'll stay here. The advantage of intrusive methods is that you can, in solving once, get the full uncertain solution, but you have to solve a larger system, and you have to rewrite everything, solvers and codes, etc. And there is an illustration in a flow field. This is now a paper that's quite old, but we had worked here on incompressible flow on a channel with uncertain viscosity. And what you're looking at are the modes of the velocity field, the coefficients, the PC coefficients for the modes of the velocity field. So V0 is the mean velocity field, and the flow is going vertically up here. So it's, you see, like it's a starting flow in a rectangular channel. So you will get an initial startup phase, and then you get the fully developed flow, which stabilizes further downstream, which is towards the top. And the individual modes are shown to the right. The one that's easiest to understand is the standard deviation evaluated from the modes, which is the rightmost figure. And you can see where you have uncertainties in the flow field due to viscosity being uncertain, and where you don't. Yeah. So this is the type of information you want to get out. So this is done one shot in solving a new set of equations. But as I said, this is the advantage, you solve it once, but there are a number of disadvantages that are shown here. I won't detail them, but there's a number of issues with these methods. They work in a class of problems, but there are other classes that they still have issues with also. All right, let's focus on non-intrusive methods, which treat the solver as a black box. These methods rely on sampling. And here, you can imagine any quantity of interest. It could be an output of the model, or it could be some statistic on the output of the model. So that's the quantity phi, and you'd like to find its PC expansion. And ultimately what you need to do is to evaluate these integrals shown here. These are the projections of phi onto the PC modes. And whereas intrusive methods apply the projection to the equations themselves, non-intrusive methods apply them to the solution effectively. And so what you do is you evaluate these integrals. To evaluate them, you need to evaluate the value of the integrand at different values of xi, and that means evaluate the forward model for different inputs, for different samples of the input. Okay, so to evaluate these integrals, you can rely on any type of quadrature methods. You can also do Monte Carlo methods, of course, but Monte Carlo still has the question of convergence. A lot of research in this area has been on developing effective, sparse, and adaptive quadrature methods to be able to evaluate these types of integrals with the smallest number of samples of C, so you don't have to solve your forward model too many times. And so these methods rely on sparse grids. Examples of them are shown here. Rather than having a dense grid on this 2D system, this sparse grid is optimal for a certain class of polynomials that you postulate the order of the system to be within. And so these types of methods are used often for sparse quadrature evaluation of these projection integrals to evaluate the PC modes of the output of interest. Okay, and these have been used in a large class of models. Here's an application in large eddy simulation of a burner that was done here at Sandia last year. This is work with others at Sandia listed above. So this is a large computation. We were doing this to look at the impact of uncertainty in parameters of the model. There's the Smagorinsky constant, which defines the character of the subgrid model within this LES computation, as well as the turbulent Prandtl and Schmidt numbers. These are the uncertain parameters, and we use second order Polynomial Chaos. We evaluate the model at 25 points only, and we have the predicted uncertainty in the output. So this is how it's used typically in any type of model. Here's an application with ocean modeling. This is work with people at Duke and also at the University of Miami. And this is modeling of the Gulf of Mexico during Hurricane Ida. And there are 4 uncertain parameters here. They include aspects of the LES model, subgrid mixing, and also wind drag, or the wind is a random field forcing here, so there's character representation for the wind drag, and the parameters of that representation come into the picture as uncertain. And so here we use almost 400 samples, so 400 evaluations of the ocean model that were required to evaluate the quantity of interest, which is what's called the predicted mixed layer depth, and it has to do with understanding the kind of mixing that's going on in ocean layers. Okay, so that's quickly over forward UQ methods. Let's talk about inverse UQ methods, where we're estimating uncertain parameters from data on model outputs. And these are important in general, any type of measurement, but certainly important for forward UQ in computations because, as I said, the inputs have to come from somewhere, and they usually come from measurements. And we need a PDF on the inputs, so we need to do probabilistic analysis for the inverse problem. So we don't want just least squares fit to get the best fit parameters. We want to get a sense of uncertainty in the parameters. And so in this probabilistic setting, a very convenient and effective framework is a Bayesian framework. And I will talk specifically about Bayesian methods here. And so in a Bayesian context, if you have data, you can use Bayesian inference to get a PDF on the parameters that define the model that you try to fit the data with. As a side note, if you don't have data, but you have constraints, and this is quite often the case, that you know something, you know maybe statistics of the data, maybe moments, but you don't actually have the data. It's either was thrown away a long time ago or you simply don't have access to it. Then you can rely on something that's quite related to Bayesian inference, which is the use of maximum entropy methods, and that allows you to do the same thing. So I won't talk about max ent here, but just FYI. Okay, so Bayes' formula is basically a simple statement on probabilities, and I apologize if this is I don't know the composition of the audience, but I'll explain it, that this is somewhat of an obvious statement. But I will also explain it specifically as regards to fitting. So if I have, in this case, a very simple model, which is take parameter lambda, it gives me f of lambda, and I'm measuring it with some instrument, then this prediction of what's behind the data is convolved with measurement noise. That's this epsilon that I have here. And the final data y has noisy estimation of this model output. And what we're after is a statement on the PDF of lambda, and that's this posterior density shown here, highlighted in the plot, in the slide. We're after a density on lambda, given that we've measured the data y. And Bayes' formula is just a statement on the joint probability of lambda y that can be written as shown very clearly, and its particular utility is as shown in the annotated equation, where we have the posterior density on the left. It's the density of lambda given data y. That's what we've learned about lambda, conditioned on having measured something. It has then on the right the likelihood, which is if I use my model with parameters lambda, what's the likelihood that I will find the observed data y as prediction. And then the prior, which is whatever we know about lambda before taking the data. Okay, so that's quite obvious. The evidence, I will get to eventually, but the evidence is basically, is just for now can be thought of as a normalizing factor, but it's really the integral of the numerator of this equation. So it's a very simple statement here. Okay, so in Bayesian inference, you want to basically come up with a prior and a likelihood, and once you have those, you have the posterior density, because, as I said, the ratio can be simply the product of likelihood and prior normalized, because the integral of the posterior has to be 1. Okay, I won't talk much about priors. Prior specifies what you know before you take the data, and I'll leave this slide without much detail. There's a lot of detail on priors, but frankly, for most physical problems we deal with, it's the likelihood that's more of an issue. The likelihood is a density that you want to construct based on your prediction of the data. So if I have a presumed model G, sorry for switching from F to G, but here I have Ym, which is my model prediction, G of lambda. And I have data Y. In general, there'll be a discrepancy between the two because of the fact that I won't be able to predict exactly what I'm measuring. And it's quite often that this discrepancy is due to mostly instrument noise, and we can model it as a random variable because it originates in noise. And for many instruments, you can be sure what the character of the noise is, and it's frequently Gaussian. So let's say epsilon is Gaussian as shown at the bottom. So given that, the relationship that we just showed says that the data is expected to be normal, centered on the model, but with variance sigma squared. And with that, you can just write a density for the data. And if you have n data points, and you know that the model is independent, I'm making assumptions here just to illustrate, but none of this is required, right? If you know you have n of these Gaussian data points and they're independent, then the full density that you're interested in, which is the density of the data conditioned on the parameters, is simply the product of the individual likelihoods, which are the individual Gaussians, and that's the likelihood you use here. Okay, but again, this has a number of simplifications for illustration. It doesn't have to be like this at all, but this is how you would typically construct a likelihood. Of course, the simple scenario that I presented is not what happens usually. Frequently, you don't know that the discrepancy is only due to instrument noise. The discrepancy can be because your model is wrong. It does not predict the truth very well. The instrument is looking at the truth and adding noise on top of that. But your model difference from the truth is another factor. And they're all convolved here when you compare your model to the instrument data. And so all of this has to ultimately enter into the likelihood. And And further, the character of the noise can be uncertain, and that has to be built in. And there's a lot of other details. But it's important to understand the basic picture, but there's a lot of challenges when you apply it to real models. You have to be very careful about these various pieces of it. Having a likelihood and a prior, as I said, what we care about is just the proportionality to the product, because the normalization can come afterwards. All we need is to estimate samples of the posterior density shown here, which is a proportional, something is proportional to the product of the likelihood and the prior. And quite often, of course, in large models, you don't have the likelihood analytically, even though you might have the prior analytically. So this has to be done computationally. And a very good class of methods to do this is Markov chain Monte Carlo methods, which rely on using a random walk to generate samples from a density without actually explicitly writing down that density as, analytically as a formula. And these MCMC methods are widely used in Bayesian inference to generate samples from posterior distributions. And the methods simply use a proposal density to generate proposed parameter values, and then an acceptance rejection rule to see if this parameter value has high probability in a posterior range or not. So basically, the algorithm simply goes in a chain, proposing at each step a new vector lambda, evaluating the likelihood and prior, and then accepting or rejecting that sample. And the net result is that the samples you are left with are samples that adequately represent the posterior density. The issue, of course, is that this is computationally intensive. You generally need many, many samples. And so here, again, you need to think of a cheap representative for your forward model, a surrogate model, if your forward model that goes into the likelihood is a complex computational model. And this is often done in statistics with Gaussian processes. It's also done in UQ specifically using, again, polynomial chaos methods, because one can presume a density on the inputs, propagate it forward, and build a PC representation for the output. And this now is simply a representation of the model output as over the range of variability of the input. So it's a surrogate for the forward model for the quantity of interest over the range of variability of the input that was specified. So you can use this in the Bayesian likelihood and accelerate the scheme, the method, of course. So you only need to take as many samples of the forward model as is required to do a forward UQ problem, but then here you use the surrogate. And of course, if the chain steps outside the presumed initial density, you can go back and make it wider or build a new surrogate, etc. Okay. And a very simple illustration of Bayesian inference on a fitting of a parabola to a set of points is shown here. So we're taking data from a parabola convolved with noise, as shown here. The noise is Gaussian by construction, and we want to fit a parabola to this data. And so basically, we want to find a joint density on parameters A, B, and C of the parabola. And I'm showing here the joint density on A and C plane, just to be able to illustrate. And we're showing three cases. The red case is with low noise, then green, then blue is with high noise. And you see the result. The true value of the parameter is 2 and 5 for A and C here. And if you have enough precision in the result, in other words, when the data noise is low, the posterior density is really tight, and you know the answer very well, you also know the location very well, right? So you know both the mean and the uncertainty in the parameters is known very well. But if you have high noise, then your answer is corrupted by noise, as expected. Both the nominal value is far away from the truth, as well as the range of uncertainty that you get is reflecting the impact of the noise in the data. Okay. I want to cover some challenges. In Bayesian inference specifically, there's a lot of challenges in large computational models. First, the posterior peaks are not always nice Gaussian single mode peaks, as I showed. Often you have multiple peaks, and so you need to make sure your method can explore that difficult density well. And so there's methods that rely on multiple chains, or what's called tempering, which basically softens the peaks down initially and then gradually grows them up, so you have a chance of sampling all of them without getting stuck in one peak. It's also important to have a very good starting point. There's also a lot of work on having good proposals and getting good chains. Good mixing is really a technical word for saying that you have samples in the chain that are not too strongly correlated, because ideally you want independent samples, but that's rarely available. Okay, and there are methods that I've listed here that I won't have time to go into that are highlighted in the recent literature. I've mentioned names below, and so there's a lot of ongoing work to make these methods efficient and effective, particularly in high dimensions. When you have a large number of parameters you're inferring, this can become a very complex problem, and there's a lot of challenges involved. Another important challenge that I will go over very quickly is model error. What if the discrepancy between the model and the data is not only due to data noise, but because the model is wrong? And there have been new methods under development here, and I'll talk very briefly about them. So I will show some results from our work where we embed model error in submodel components where we know we've made approximations. And specifically, I want to show a picture where we're fitting data with a model. Okay, and this is first a classical Bayesian picture where you do not account for model error. And in this case, we have a truth function that's red, and we generate synthetic noisy data from it, which is the black dots. And then we try to fit this data using a polynomial. And the best fit polynomial is shown in red, and then we have the gray bars that show the uncertainty around it. And in this case, which is the classical picture without model error, as you take more and more data, the uncertainty in your predicted model is simply smaller and smaller, because as you take more data, you learn more about the parameters, you reduce the uncertainty. But you can see that the resulting model, even though it's wrong, we think we know it very well. We have a really good prediction with low uncertainty, but in fact we're off. You can see that there is a distance between the model and the truth, which is in red. What we're after with model error representations is to capture that discrepancy within the predicted uncertainty, to be able to predict with uncertainty that has in it model error. And that's what our method can achieve. Of course, I haven't highlighted it, but the citation is in the slides. The same picture now including model error. And when we take more data points, while the uncertainty does shrink, it doesn't shrink indefinitely. You can see it still stays of the order of the size of the model error. The discrepancy between red and blue lines is within the range of shaded uncertainty. And moreover, we can discriminate between data error and model error. And as you take more data points, n more data points, the data error component of predicted uncertainty is shown in red, continues to shrink as you would expect with more data points, less predicted uncertainty resulting from data error, but the model error component stabilizes it at a given value. It doesn't matter if you give me more data, I'm fitting with the wrong model and I will have residual prediction that's wrong, and this measure of uncertainty in the output is capturing that residual. That was the intention of modeling data, model error in the inference. And very quickly,
thank you very much,
I will talk about model evidence.
Good introduction to the topic. There's certainly a lot to think about.
So
here.
in general, you might have a set of models of interest. And you can do all of this fitting that I mentioned with one model or another. For example, I could have fitted that data with a cubic or a quadratic or a linear model without knowing what the truth model is. So everything we've talked about is conditioned not only on the data, which is shown here, but also on the model NK, right? And you can evaluate the evidence, which was that denominator in Bayes formula, for each model separately by doing the fitting with Bayes formula and evaluating the integral of the likelihood times the prior. And that's shown here in the estimation of the marginal likelihood or the evidence for the model NK. And this evidence is useful for making choices among models. This is a very important point. It's useful for finding the model that's most consistent with the data, and also on choosing a model that's robust, that doesn't have too much complexity, that's not justified by the amount of information and the data. And there's a quick illustration of that here.
Yeah, that sounds like
so here we're
those
generating data from a
while we're waiting
a cubic model shown
I want to remind
in blue.
people
The data
that
is in these blue dots,
our
and the
next
true model
webinar
is
will
dashed
be on March
blue.
10th,
And then we're fitting it with different models, and we're showing the fitted model with
starting with Anna
uncertainty
Michalak
on
from
top
the
of
Carnegie Institution of
the
Science,
data.
and she'll
And
be looking at
we're going
characterizing
to look
complexity
at
and
fitting with
quantifying
different order,
uncertainty
going
in
from first
environmental
order and
systems.
up. So
The
more
goal
high and high
improving
order
our understanding
polynomials.
of these systems.
And
So we invite you to come
clearly,
back for that
order
talk,
one
where
is
we
not
can look
a
at
great
some
fit to the
applications
data. Order
to
two is a
Earth
little bit better.
systems.
Order three is on top of it.
I don't see any
but
questions
in principle,
out
you don't
there,
know
so
what
I
the
want to
truth
thank
is,
you
and
again very
you
much,
could try
Habib, for taking
different
your time
orders.
out this
So
afternoon
if I go
and
to
giving us
higher
this
order
talk.
and adding
And
complexity,
thank everybody for joining us.
as I go to more and more complexity, you can see that I can start forming wiggles. But because what's